Good morning. I am presenting my embedded system internship project, the electrical vehicle ADAS and telemetry dashboard. In this project, bridges low-level hardware controls with high-level software. I programmed and simulated on ARM Cortex M3 microcontroller, the STM32 Blue Pill, and connected it to a custom Python dashboard. It simulates a modern electric vehicle and displays real-time safety warnings, driver inputs, battery status, and thermal limits. In the modern EV industry, demand has between safety sensors and dashboard displays. My project implements three primary goals. The first one would be the ADAS warnings, where it uses ultrasonic range sensors. We aware active side blind spot monitors and front collision warnings. It alerts and make LED lights if an obstacle enters in the safety boundary. And the second one would be the fault protection system, where we monitor key parameters where a system fault is triggered. If the battery SOC falls below 15% or monitor temperature exceeds 100 degrees Celsius or a sensor get disconnects. We also build a brake override system that flags a fault in the accelerometer and brake pedals are both pressed less than 20%. And the third one would be the telemetry and visualization. All metrics are serialized and streamed into a graphical dashboard, providing speedometers, radars, and battery controls. And coming to the software tools, here for software we used STM32 CubeIDE to compile C code firmware and PICSimLab to simulate the blue pill board and VSPE to create a virtual serial bridge where I used COM1 and COM2. The dashboard UI was programmed in Python 3 using Tinker. And in the hardware components, I have used several peripherals on the microcontroller. And the first one would be the ADC one, where it read analog sliders like throttle, brake, SOC means state of charge and temperature on PA0 to PA3. Pin 1, a 1 megahertz based timer where I used a prescaler of 7 Emertxe, providing microsecond precision for echo punch. And for UART, where I configured at 11,200 bps to stream formatted telemetry to the Python router for the 1,15,200 bps. GPIO port where I handle trigger and echo lines and the drove alert LEDs from the connections from port BB8 to CB11. And now if I look into the system architecture diagram, on the left side we can see the STM32 blue pill where it executes the firmware polling load. It triggers the range of sensors, perform ADC on the slider inputs, evaluates safety rules and controls warning LEDs. In the middle you can see USART serial telemetry link transmitted formatted ASCII 11 strings over the virtual COM bridge. And on the right side, you can see about the Python dashboard. It runs a threaded serial reader to prevent GUI lag. Telemetry is processed by a physical engine which calculates speed and torque based on the throttle pressure, which is given by the user in this case. Monitors the battery charging and the regeneration state as well, and reads the indicator for every 100 milliseconds. Now I will demonstrate the live stream of the PICSimLab simulator running in my system. Now you can see this as a blue pill board. First thing, we should need to open the file and we should load the bin where I actually uploaded it for itself. And now we should even configure it with the Python dashboard. So we should go to configure And now in the serial port, you can see as it COM1. As I already did it before itself, so it's automatically in the COM1. And you need to click on save. Now you will actually open your spare parts. Now you can see this as a virtual terminal, and these are the three ultrasonic sensors, where the first one would be the front sensor, and the second one would be the left sensor, and the third one is right sensor. And now here we are going to control the values as we don't have the hardware as well. And these are the faults. So first we'll be looking into the virtual terminal. When I click on it, hmm, now you can see those values in the PICSimLab terminal. See, if you want, we can notice the values for the front sensor, it is almost 360, and for the left sensor, it is 333, and for the right sensor, it is showing 353 and 354. And okay. Now, if I reduce in the left sensor, as I kept at 188, you can see it at 180. And now, if you go to the right sensor, again, I'm reducing it. You can see here at 127, 128, a little bit. Now, even for the front sensor, you can see 179, 180. Now, if I reduce the left sensor completely, like below 20 or 30, um, then you can see a left sensor blinking, which means the object is very near. And if we increase the left sensor and decrease the right sensor value, then we can see the right sensor is blinking as the object is coming nearby or the vehicle is coming nearby. And if you reduce both the values, like if you reduce the front sensor, then it seems to be like it's very low. That's why it seems to be like collision is going to happen and it's giving a warning itself. Um, now we'll go to the Python dashboard itself. First, we need to run it. Here is a Python dashboard. First, we need to select it to COM2 and connect. So here, these values are based on this. Now I'm reducing it. The speed and like acceleration I'm reducing, so it's slightly increasing. Now if I increase the brake, then automatically the speed is getting reduced. Now again I'll be increasing it. So you can see it's increasing and even the range of kilometers is getting reduced. 875, 874. Now if I'll increase the speed, it's going till 61 and it's going more as 4. Now I'll be reducing the speed and increasing the brake. You can see the range of kilometers are increasing. So 850 to 853. Now I'll be reducing the left sensor value. So you can see it's going blind, like it's all a vehicle is almost near to 9 to 11 centimeters it's showing. I'll be increasing it and I'm decreasing the right sensor. So if now it's no right sensor is showing the 10 centimeters level. Now I'll be reducing the front sensor too. So you can see like it's giving a warning that its collision may happen, and it's showing 50 centimeters. If you see it here, it's 50 to 50. Mm. Other thing, state of charge, like that. And now you can see even you can flick the charger, like the battery is getting charged, and it became normal after 100. Now it would be a telemetry dashboard UI and its integration. Uh, first, my two core EV behaviors would be plug-in charge, where it gets toggled on click. Like if we click on the plug charging, it gets charged. And once it reaches 100, it automatically gets disconnected. And the second one would be the regenerative braking. And if the vehicle is in motion and the brake is applied, the dashboard calculates the local energy reclamation and charges the battery associated. And my Python dashboard display the vehicle speed and torque, plotting speed on a rolling history chart, and the center ADAS bird eye view that draws active warning zones and blind spot blocks based on proximity data. Now coming to the key learnings and the skills required would be MCU architecture or the firmware, where we configured GPIO registers, time decouplers, and managed ADC conversions under HAL. HIL debugging, where it solves simulation timing errors by masking interrupts during pulse captures. Telemetry communication, bridge telemetry frames over UART using a background threads in Python. GUI design, learn layout constraints and fixed with formatting to eliminate tinker label, wiggling and layout wiggles. Now we'll seeing about the conclusions and features. In conclusion, I successfully designed a closed loop ADAS EV simulation with a stable telemetry UV. The feature scope would include hardware development where flashing the firmware onto a clearistic physical STM32 blue pill development node connected to physical sensors. And the second one would be autonomous emergency braking, where you can update the firmware to override the throttle and apply braking force automatically if the front collision warning is triggered. Thank you.